All right, Vishaki, I think you need to share the screen.
Can you see the screen?
Yes, I can see it. Let's take a couple of seconds and then we'll start.
Sure, sounds good.
All right, let's start.
Mm-hmm.
Hello and welcome to today's ACM SIGSOFT webinar. This webcast is a part of ACM SIGSOFT's commitment to provide value to its current and future members. The ACM SIGSOFT webinar series features speakers from the Future Software Engineering track at the International Conference of Software Engineering, as well as select keynote speakers and distinguished paper authors. I am Shoykot Chakraborty, a senior researcher at Microsoft Research, and it is my pleasure to welcome you today. Before we get started, I would like to quickly mention a few housekeeping items shown on the slide in front of you. If you have any question during the webinar, please type them into the Q&A box at any time during the webinar. At the end of this presentation, we will have time to respond to questions. This session is being recorded and will be archived. You will receive an automated email notification when it becomes available. Next slide, please. Today's presentation is Programming Language Processing, How AI Can Revolutionize Software Development by Professor Boishakhi Rai. Professor Rai is an associate professor at the Computer Science Department at Columbia University, New York. Her research interest is in the intersection of software engineering and machine learning. She won IEEE TCSE Rising Star Award and NSF Career Award and Best Paper Awards in several software engineering and system conferences. She is also a visiting academic at Amazon AWS. So, Boishakhi, without further ado, take it away.
Thank you, Shoykot, for the nice introduction. And as Shoykot mentioned already, today I am going to talk about programming language processing. It's a new emerging field with a lot of excitement around us. And I particularly will focus on how this new PLP or programming language processing field can revolutionize software development. So in today's world, software is everywhere. We directly and indirectly use software all the time, almost in all aspects of our life. To support the production and maintenance of such huge software demand, developers put enormous time in developing quality product. For example, their first job start with coding some feature, either from scratch or adding some new features in the existing product. Then they write test cases to test the feature that they have implemented. If unfortunately they find a bug, then they have to analyze the code to find bug. Then they have to fix the bug, and finally they have to write documentation, either in code comment or document like about explaining the code to what they did for increasing maintainability and readability. And this slide shows only a small snapshot of developers' day-to-day activity. There are many other things involved in a regular developer's life, including binary analysis, security analysis, running test cases, also meeting, email communications, etc. So to improve software development, there have been a lot of research from our community that focuses on improving software development, and in this way also improve the software quality. So there, the main techniques that we propose from the community are largely can be divided in two classes. One is recommending different human practices, or technical solutions like bug finding tools and things. So, there are enormous amount of bug finding related tools that are proposed over the decades, starting from static analysis, symbolic execution, then dynamic analysis, fuzzing, etc. Then there are automatic code editing and bug repair tools. From more human aspect, we recommend best coding practice, like we have to review our code, there should be regular patch update, and there are many team processes that are proposed. However, in spite of all such effort over the decade, we still see a lot of bugs are coming in everyday software development. So for example, we did this study a few years back with around 728 projects across 17 languages. And we found that 36% of the main branch commits of GitHub are related to bug fix. And I would like to remind us that all these projects that we chose are important projects that are curated based on their stars. So I hope they have gone through some of the recommended practices that our community suggests. So 36% of them are related to bug say something. And more interestingly, we also did some analysis what kind of bugs are coming, and we found that along with common bugs that we know all about, like security errors, concurrency, performance, etc., to our surprise, 88% of those bugs belong to plain programming error that we could not categorize to any common type. So these errors can be incorrect error handling, incorrect API usage, specification error, even typo errors, copy-paste error, faulty initialization. So this kind of shows something is going wrong, and there is clearly a gap between research and practice. So in many of our research, here again, from our community research, we many times find that developers often incorrect or underuse the utilities available to them. So though all these tools are proposed from the academic community, they are not well used by the practitioners. So here is one small example, again a very typical example, but there are many of such category. So template-based bug finding and bug repair is very common. There are huge amount of research has gone in this topic. But say I have a very simple code where super.equal Martin Red is bug, and its fix will be this equal to object, which is marked in green. So I, as a researcher, gave this pattern to my tool to find this kind of bug and implement the fixes. So my tool is smart enough, and it can find this pattern, and then it replaces it, and my code is fixed. Now what happens when there is a slight different variance, and instead of equal, now my code content n equal, which signifies to not equal. And given I gave the pattern equal, the template-based tool will not be able to find this kind of slight change. So as you can see, The template-based research has low tolerance for deviation, and also it is clearly humanly impossible to write every possible patterns that can be related to bug and fixes. So what I am trying to say, the success of these tools depends a lot on human judgment, and they are not scalable and requires a lot of domain expertise. So the goal of my talk is how to automate more towards better software development. And as we start thinking about it, suddenly with the emergence of GitHub, Bitbucket, this lot of software engineering related data started becoming available to us. And then many researchers started calling them big code, which is the big data equivalent for software engineering data. So with such enormous opportunity, we can now record all software engineering related activity. So of course, we can record code and code related metadata. However, we can record all the bugs, the email and chat conversation, user reviews, question answer forums that the developers are getting. And once we record all these whole software engineering communication and development, now this new emergent field that I am calling programming language processing, or sometimes it is also called AI for software engineering, is emerging, where we first curate the data from this plethora of software big code data. Then we design neural network model or machine learning model to learn from this data. We train our model, and then leads to this AI-based automation tools. And there can be many such tools like bug finding, code generation, and whatnot. And we will cover them as we go through the talk. So as we have seen in huge body of clone detection and many such related research, that software is in general very repetitive, and not only software, the way it is edited is also repetitive. And AI-based modeling showed huge promise to automate such task where there are a lot of regularity in my data. So a lot of researchers, including us, when we realized this promise, we started taking off-the-shelf machine learning models and tried to incorporate it in code corpus and get some initial benefits. However, I would like to emphasize their code is a little bit different from text, and let's see how code is different in many aspects from text. So first, code has lexical properties, so which is probably the most related features to text. So it has variable name, keywords, etc. However, all these variable and keyword have different lexeme types. So either they are identifier, they are keywords, etc. And also code has open vocabulary, right? So we can give any name to the variable and the code can still be semantically correct. Then code has huge syntactic structure. So for example, this small piece of while loop has a large tree structure. We typically call it abstract syntax tree. And on top of that abstract syntax tree, there are all this data dependency, control dependency, and whatnot we can put on to make this structure even more formal and then grammar aware. So with that comes the syntactic correctness. So even if this piece of code looks apparently correct, because there is a small grammar violation, Here, if is a keyword, and if cannot be treated as an object, this code becomes syntactically incorrect. And while we are thinking about code processing, we need to think about such kind of syntactic constraints. Not only that, code also has some contextual correctness. So for example, again here, my function is f, and in this if statement, I am trying to compute an element with the same function, which is most likely giving type error because they are not similar type. There is another problem where this function f is returning Boolean, but in this statement, I am returning null. So it is also contextually incorrect because it will give me type error. Code has huge semantic property. By semantic property, I mainly mean input-output here, but it can be also dependent on your environments as well as configuration, etc. So for example, in this simple while loop, if I change x less than 0 to less than equal to 0, it is the code changes significantly. So with slight syntactic variation, the semantic can change. Similarly, if I change the variable names and minimize the code considerably, as shown in the gray box, we can still see these two while loop are still semantically same. In contrast, natural language can by default, by design, can tolerate a lot of ambiguity. So while designing code model, we have to think about such a more formal nature of code. And last but not least, code has execution properties, right? So these two pieces of code behave very similarly, and without understanding how these opcode behave, like how move, XOR, add, etc. behave, we are not going to understand that they are very similar code. Understand the semantic that code in, when we look at a code corpus, there like code comments, bug source code binaries, execution traces, sometimes configuration options, etc. So with such diverse different properties and diverse modalities, while thinking about code, we have to think about all these modalities as well as, and also code has an evolutionary nature, right? Because code changes all the time. So with these different modalities, we have to think about the lexical understanding, like in terms of lexeme, tokens, etc., semantic understanding, input-output behavior, as well as the syntactic structure. So nowadays, the machine learning model or AI-based technology try to process code or analyze code using pre-training and fine-tuning model. So these models try to understand a generic representation of the code. So given I have lexical structure and semantics property of the code, we build a neural network that overall learn the generic properties of the code without any task-specific details. And then we transfer the pre-trained model for more task-specific details like finding code clones or bug finding or generation. So this kind of pre-training and fine-tuning paradigm becomes very popular, mainly because of its advantage that you can get as much data as you want from the open source. Because they are task agnostic, we don't need to annotate data. They can be further adopted in different kind of code specific tasks, and in that way they are very generalizable and lot of data can be used. So with this kind of infrastructure of modeling in mind, in today's talk I will talk about mainly two topics on how to build code property aware models. I will talk about how we can leverage more static code properties in our modeling. And I will also talk about, briefly mention how we can leverage dynamic code properties too. So first, let's see the static code properties. So in modern day, when we think about code modeling, usually BART-like architecture becomes very popular, where BART-like architectures are a stack of transformer models, a transformer encoder with self-attention layer. So given a code or a piece of, say, a function or piece of code, first we flatten the code in a code vector, and then we randomly mask the tokens, and the mask language model becomes very popular, where the mask language model's job is to predict the tokens that are masked. So that will be the output of my transformer models, BART-like transformer models. And finally, we take the code embedding from the last layer of the transformer, and that embedding can be used for many downstream tasks. So this kind of code embedding becomes very popular nowadays, and it shows promise in many downstream tasks. However, while thinking about code, we have to think whether this purely text-based model, because as you can see here, we treated this piece of function as like sequence of token, just like text, whether they can reflect real code properties. So to understand that, we first ask this question, whether they can identify two functionally similar and dissimilar code. So for example, look at this code. They are taken from open source FMMPEG code, which is a fairly popular library for image encoding. And apparently this code looks very similar, with textually very similar, with certain functional differences, because the float value in the original left-hand side code has been changed to integer. And in fact, this was source of one integer overflow vulnerability. So as you can probably realize now, if the code embedding model puts these two pieces of code in the similar embedding space, then the downstream model will not be able to identify the right-hand side code as bug, and a good model representation should be able to recognize it. Similarly, look at the same code where I changed the variable names, function names, as well as the permutated some of the independent instruction. And as you can see that here, the code textually look very different. However, functionally, they are similar. So again, a good code embedding should be able to identify, though these two code are very different looking, they are functionally same. So with this motivation, we built a model called DISCO, where our loss function, when we designed in the model, we use a contrastive loss function, which essentially says that two similar piece of code will be together and two different semantic code will be different. So we use this model for two tasks, clone detection and vulnerability detection. So at a high level, we have our original code. We first injected bug in such a way that the code looks still semantically very similar with subtle difference. And we also synthesize code so that they are semantically correct, but textually they are very different. With that, we design our pre-training task where the positive examples are close in the code embedding place and negative examples are pushed further apart. And we show that our model takes significantly less pre-training data because it is code aware and it achieves state-of-the-art performance. So in terms of process, we first took our source code, analyzed the abstract syntax tree, then we inject those patterns, and then we generate these buggy and clone patterns. And then in terms of buggy pattern, we actually motivated the buggy patterns by studying code vulnerability database, CVE. So for example, we injected misuse of data type. We injected misuse of pointer, then misuse of variables, a removal of conditional statements, which is one of the common vulnerability cause of vulnerabilities, change comparison operators, as well as misuse of values. So these are called our negative samples. For generating positive samples, we change the variable renaming, we use function renaming, as well as we did statement permutation. So with that, we design our model, pre-training model, where we have masked language model for the token understanding the lexemes. The NT-MLM is the structure-aware model where we learn the structure of the AST type of each node, as well as the contrastive learning, which learns the semantic similarity and dissimilarity of the code. So as I said earlier, we use this model for vulnerability detection and clone detection. So we fine-tune this model with much less data. And let's see some of the results. We use codex, glue, and reveal, and we look for precision, recall, F1, and accuracy, all the standard measurement. And as you can see here, the DISCO, which is our model, perform at par or slightly better to the existing state of the art. But interestingly, I would like you to see the code size. While the state-of-the-art models were taking 20 gig to 160 gig data, we achieved this result only by using 1.8 gig data. And in clone detection also, we found similar result. We performed comparably with using way less data than the state of the art. And moreover, when we improve the data, increase the data set, so we used up to 13 gig as compared to 20 gig, which is our one of the baseline. Across all the tasks, we outperform the baselines. So this shows the potential of designing code-specific code-aware properties in the model to not only make better model, but also you can make much more efficient model and green model as well, which becomes very, important term in nowadays for AI modeling. So we leverage this kind of semantic similarity concept for code generation task as well, and we design NatGen. So here we have this correct original code. We use noise injector and make it is a noisy code, which is basically a semantic variant of that original code. So I am not going in details, but later I would like to refer you to our paper, or I can talk more. But at a high level, this is an encoder-decoder model where the encoder takes the noisy code, and the job of the decoder is to denoise, which is basically the NatGen model, to decode the correct code. So in this way, the NatGen is designed to learn the semantic preserving mutations. Some of the semantic preserving mutations, like we have the original code, we change the while loop to for loop, then we change different type of for loop or insert dead code. Again, we did block and operand swapping. We did injected confusing code element, as well as variable renaming. So very common kind of semantic variants that we can often find in the code corpus. And in this way, we generated 8 million code examples across 8 languages, which is still way lesser than some of the big code model that we know, like Copilot, etc. So for NatGen task, we started with Code-T5 model, which is again a very popular open source model, came from Salesforce. We use code search net dataset as our original code, and we checked the NatGen's performance in text to code generation task, code to code generation task, as well as text plus code to code generation task in terms of bug fix. And as you can see, at a high level across all these tasks, NatGen outperforms its predecessor. But the most interesting part here is when we use NatGen at 0 shot, like that means we don't have any fine tuning. We did not do any fine tuning on those particular tasks, like say bug fixing, code generation, etc. We can still see that CodeGen with NatGen, which is marked in blue, is significantly outperforming its predecessor, like its baseline. This kind of result shows across all the tasks. And this kind of result shows, given we design the pre-training with a more code-aware property, NatGen can learn code-aware properties and can transfer it for task-specific tasks. Similarly, when we use NatGen with a few shot setting where we train it with 200 examples, it continues to be outperforming the baseline, which is Code-T5. And here it shows that while NatGen's performance is somewhat testable up to 500 few shot settings, you have to give more and more fine-tuning examples to the other kind of baselines, like Code-T5 in this case, so that they can slowly match NatGen's performance. So in this way, we can see that code-specific properties to design even encoder-decoder helps to teach the model in a much efficient setting, as well as they perform better. So with this, now we see that how we can design static static aware code properties for modeling. Let's see a little bit how we can leverage dynamic code properties in the modeling. So here I will explain our work in binary corpus, because binary corpus is very important for many security analysis tasks. I wanted to show that how code modeling is used. So far we discussed source code modeling, and here I took a different kind of corpus or which is binary, and see how binaries can be modeled with machine learning. So before we go there, binary modeling is very tricky because all the variable name information got lost, the binaries are stripped, as well as here you can see the same code which are compiled in x86 and ARM, and they look completely different. So we need to understand the semantics of this instruction like AND, CMP, LSL to understand that these two pieces of code is similar. Not only that, when we compile a source code across two different compilation flag, like optimization flag, they start looking very different, so it becomes more complicated. And last but not least, if you slightly, across different version of the code, the semantic can be changed as well. So the message I am trying to give that for binary modeling, it is very important to understand the semantic of these operation and operator to make the modeling work. And only by looking at static code property, we cannot understand that. So for binary modeling, we first took some instruction and their corresponding traces. Now for generating traces, we use as micro traces. By micro traces means we randomly took a function and randomly initialized its parameter with random values and let that code run. So the idea is that though that execution trace may not completely reflect the global trace, like if you train the model from the beginning, but still it can capture very well local property because you are running each function at a local granularity. So we took such micro trace, aligned these traces with its corresponding instruction, and then we are trying to learn these operation semantics, like what does add mean, what does subtraction mean, what does jump instruction means, and so on. So this is our pre-trained model. To do that, we first took the instruction sequence and trace values and aligned them. We also took the memory addresses and put the memory addresses as a different modality. And we also indicated that whether a branch is taken or not by, say, taking the Boolean feature of yes and no. So these are then four modalities of information we used in our trace-aware modeling: static code, execution trace, memory layout, as well as control flows. And then we also took some auxiliary feature like different opcode and operand position as positional encoding, as well as the architecture. So we again use a transformer kind of model where we first embed each token from each sequence and aggregate them in a vector sum. Then we leverage the self-attention layers from transformer to learn interaction between instructions and their execution traces. In order to force the model to reason about execution behavior, we design the training objectives that asks the model to predict random masked values. So for example, here we ask the model, we mask in a position so that the model can reason about forward computation, like 2 minus 1, what will be the value, and it understands subtraction semantics. Similarly, in this example, we teach the model to learn backward. And in this different combination of exposing the model for operation semantic, hopefully the model learns what computationally a subtraction operation or an addition operation means. So we use this kind of pre-training for many binary analysis tasks. And we showed that across many tasks like matching semantic similarity, type inference, and memory dependence, it gains huge improvement. And not only that, in terms of efficiency, it got order of magnitude speed up. Also, this kind of code error modeling is much robust because now across many architecture, compiler, as well as optimizations and obfuscation, these kind of fine-tuning tasks are robust and we can get very good accuracies. So with that, today I talked about how we can build code property aware AI models. In particular, I talked about how to leverage static code properties in encoder model, as well as encoder-decoder model for generative task. I also briefly talked about how we can incorporate dynamic properties for code understanding tasks. So, and we showed that across many downstream software engineering tasks that developer use, we are outperforming the only textual models. So the question is that what's next? So AI-powered coding assistant model is knocking at our door, right? We all know about GitHub Copilot, Amazon Code Whisperer. I am part of that team as well. So that is great. That opens up a huge future for automatic coding and software development in general. But the main problem with these kind of tools as of yet is that they do not come with any guarantees, and several controlled studies in academic settings actually found that in spite of all these hypes, the developers do not trust this code very well, and it is not very clear in complicated code setting how well this kind of coding assistant tools are really helpful. So here I would like to think a bit more on this trust, like how from us, like software engineering community, we can provide more trust, we can develop and build more trustworthy aware models for different kind of code analysis tasks, and how in general we can empower software development, AI-powered software development. So if you think about code generation, traditionally we used to think about in a formal analysis way, which comes with a lot of guarantee, but they are not scalable, as well as they are, as we showed at the beginning of my talk, they are noise intolerant. In contrast, the probabilistic models or machine learning powered models, they can be scalable, they are transferable, but they do not have any theoretical guarantee. So it is probably time to think about what is the middle ground, like how formal analysis can help probabilistic modeling and vice versa, so that we can get best of the both worlds. There are several other things we have to think about. How we can feedback, like how we can incorporate developers in this whole code analysis chain. So for example, when a model predicts something, or say, for example, a model is generating tasks, if something goes wrong, how can developer give more feedback to make these models more smart? And how in this entire, like from code generation to testing to bug finding, bug fixing, in this entire software development chain, in developer and models can can work in a peer programming setting. And finally, we have to think about explainability. When we say something, hey, this software looks buggy, unless we explain or show developer these are the reasons I think this software is buggy, developers are unlikely to believe that. So we have to start thinking about how, if we are using this AI powered model, how we will provide explainability in a user-friendly manner. So with this, I would like to thank all my collaborators, advisors, and all my students. Many of the work that I presented today is led by Shoikat, who is the moderator today. So a big thanks to him. And I also want to thank my industry partner, AWS, IBM, and also NSA for funding this work. And with that, I am ready to take any question.
Thank you, Ushaki, for this amazing talk. We have several questions from the audience, and with this, while we are answering some of the questions that have been asked already from the audience, if you have any more questions, please feel free to write those in the Q&A box. So our first question is, how do you come up with the 5 properties of big code? Is it based on observation?
Right. So, yeah, that is mostly based on observation and domain knowledge. Because say when I think about code analysis, I say how compiler analyze code. They usually have this phase where you have lexical analysis, that syntactical analysis, and then compiler optimization goes for things about code semantics as well. So mostly based on this traditional way of looking at the code, but definitely there are way more properties that I have not mentioned, like how you think about energy-aware code or fairness, which code is more readable and things like that. Again, these are very traditional properties that we often talk and think about, and I came up with that.
All right. So our next question is, I think a really interesting feature to build more trust in an AI tool that points to bug like SonarQube, but more advanced. And a follow-up on that is that, do you plan on such features too?
So yes, of course. I mean, I think that this kind of points to feature or kind of relates to also this explainability, right? It is taking the important features to point to the bug that we are, to incorporate the locations that are important for the bug. And in that way, we can also think about how we can present those kind of knowledge to developer to find, hey, with this model, my sophisticated model, I have a better bug localization method. And not only that, now see, this is the reason of, this kind of location are responsible for these bugs, and that will help the developer to build more trust on your result.
All right. Our next question is, I think this question is with respect to NatGen. The question is, how is this different when compared to OpenAI Codex?
Okay, so as far as we know about OpenAI Codex, that's the model is first of all different, because I want to go to the NatGen model. Just bear with me. Okay, so the NatGen model is a encoder-decoder architecture, where the OpenAI is a decoder-only architecture. So by encoder decoder architecture, we first encode the code and then teach the model to decode as well. So that means, architecturally, it is very different. Now, if you have only decoder only architecture and they train with way larger data set than us, so in that way, definitely because of the capacity, big model and large training data, their decoder only model is very powerful, as we know. But here we wanted to show that how you can capture, like encode and decode in a more code property aware way with much smaller data set, and still can get reasonably good performance in many tasks, as I said, not only natural language to code, but different setting like natural language to code, code to natural language, and so on. So yeah, I would say the architecture as well as the way we design the noise is a major difference.
All right. Our next question is, could you suggest any existing framework for evaluation of code prediction from the perspective of the developer rather than the heuristic, that is the accuracy?
That is a very good question. There are some, I think this is an open research question, and to build a metric like what developers really want, especially from this AI assistant model, I think that would be a very good research project in itself. I don't know any such work for AI assisted code modeling on top of my head. And the reason I am using AI assisted code modeling, because AI assisted code modeling for code generation comes with different kind of interesting combination. For example, if we just take top 1, is it the right metric? If I just take top 5, is it the right metric? How the code generation performs if my context is very noisy? How much context or how much hints I will give to make the code generation better, and whether developers really like that. So I think these are kind of a very different way we will start developing code, and taking developers in this chain. And this is one of the reason in my future work, I think, as I mentioned, like taking developers in this whole process and continuously getting their feedback and building metric will be really the right direction to go.
And also to add on top of that is that all these AI assisted tools for software engineering are aimed at the developer. So wide plethora of research should be directed to how actually human developers are perceiving what is actually coming out from the AI, be it a generated code, be it a suggested bug, or be it a fix for a suggested bug. Until the developers fully adapt this or get fully accustomed to these AI models, some of these works will actually be just academic work.
Yes, yeah,
it will not show
agree.
the exact development environment.
Also, I think another very interesting research direction would be how to represent this code to the developers. Like when I say a code embedding and this embedding looks buggy and this is not, this does not make any sense unless you show the right kind of visualization. So that will become very important too.
Absolutely. So our next question is that, is any work being done in converting mainframe assembly code to an object-oriented language like C# or Java?
Okay, so that's a good question. I think this is reverse engineering problem, and this kind of reverse engineering, we did in our paper, you can have a look, that some of the small reverse engineering, like say generating function signature and things like that. And then I know there are a few papers from CMU. They looked at the variable, how to extract meaningful variables from assembly code. But this is a notoriously tough problem to get the whole code back. So basically, full transformation from code, like assembly code, to your source code, be it like object oriented or not. There are traditional tools which give some very noisy kind of source code just for analysis, but do not for code understanding. So this is again a very important research area for full transformation, and small steps we are making in different font. And yeah, this is long way to go. But this is
Also,
probably very difficult task to achieve as well.
absolutely, because with the presence of all this optimization and obfuscation, everything, the conversion from source code to binary, it's a lossy conversion. So
Exactly.
regain those losses, that itself is a very tough problem. So we have another questions, which is kind of a follow-up on the previous discussion we are having. Would you say that the adoption of such AI-powered tools significantly increase developer productivity or lowers project management cost? If not yet today, then in the future? That's
So
the part of the question.
Right. Okay. Thank you. That's a very good question, actually. So there is a AI blog from Google, and Google had their internal AI powered coding assistant tool, which is in production, and they reported that they are already increasing around, if I remember correctly, around 3% developers productivity every day. So at Google scale, every day increasing 3% productivity is not super bad. So of course we will aim more, and I am sure, because this kind of research has just started. But I think over the years, if we integrate all these kind of more guarantee, more developer feedback, we will eventually reach I feel to a point where lot of repetitive tasks, which which has less cognitive effort, AI powered tool can be able, should be able to do. And then developers' job would be to do more interesting cognitive work, like say, write the core logic or write the more like architecture, and then the code can do the fill in the gaps and things like that, at least in the short-term future.
All right. I am afraid we have run out of time today. To the audience, if you have more questions which hasn't been answered, please feel free to reach out to Professor Bushakire. I'm sure she would be happy to answer your questions. And I would like to thank Professor Bushakire again for this informative presentation and insightful answers to many of the questions. And a special thanks to each of the participants for taking time to attend and participate in today's webinar. This webinar was recorded and will be available online in a few days at www.sigsoft.org/resources/webinars.html. You can also find announcement on upcoming SEM and SIGSOFT webinars and other SEM activities at learning.sem.org and www.sigsoft.org. On behalf of SIGSOFT, the speaker, and myself, thanks again for joining us, and I hope you will join us again in the future. This concludes today's webinar. Thank you all.
Thank you for coming.